Okay, I'm going to do another example from um, section 4.3. And we're going to graph this function using derivatives. This is not a polynomial. Okay, so the first thing we usually do in order to graph the function is we find the intervals on which the function is increasing or decreasing, which means first I need to take the derivative of this function. Now I want to find the critical numbers of this function. It's clearly undefined when x is 0, so the derivative is undefined, so 0 is going to be one of our critical numbers. We also want to find values where the derivative is equal to 0. When is this equation true? Well, it's going to be true. So I have to solve this equation here. And the way I'm going to do it is I'm going to take the LCD of the denominator and I'm going to multiply both sides of the equation by the LCD. There are other ways of doing this, but I want to do it this way because I feel like it has a more general application. Okay, so I'm clearing out this fraction, and on the left-hand side I get 2 minus the cube root of x is equal to 0. Now here I'm assuming x is not equal to 0 when I do this. And this leaves me with 2 is equal to the cube root of x. Now I cube both sides and I get 8 is equal to x. So at this point I know that my critical numbers are equal to the set 0 and 8. This is where the derivative is undefined. This is where the derivative is equal to 0. Next, I need to figure out where my function is increasing or decreasing. So I'm going to test the sign of f prime. In the intervals between the critical numbers. So if I take the number -1, f prime of -1, well, I can look at this and I can see I'm going to get -3, which is negative. So the derivative is negative in this interval, sorry. I'm going to test the derivative at 1, and I can see 2 minus 1 is positive. So the derivative is positive in this interval. Next, I'm going to take, let's say, 1,000. F prime of 1,000. Clearly, if x is 1,000, this number is going to be much greater than 2. So that 2 divided by this number will be less than 1. So a number less than 1 minus 1 is going to be negative. Okay, so what this tells me, this is the sign of f prime. What this tells me about f by the increasing decreasing test is f is decreasing here, increasing here, and decreasing here. So my answer to the first part A is that f is increasing on the interval 0, 8, and f is decreasing on the interval -infinity to 0, union 8 to infinity. Okay. Part B asks me to find the local max and min. So I'm just going to apply the first derivative test. By the first derivative test, we have that at this critical number, 0, the derivative went from negative to positive. So that means that that is a local min, because the function goes from decreasing to increasing. Let's see, f of 0. Now I plug this back into the original function. So I have 0 to the 2/3 minus 0, so that's just 0. So that's my local minimum value, and it occurs at 0. And we can also see that at this critical number, the derivative changed sign from positive to negative. So this is a local max. And I'll say of f of 8. F of 8 is equal to, so the cube root of 8 is 2. 2 times 2 is 4. So 3 times 4 is 12 minus 8 is 4. Okay. So that's my local maximum value. Next, I'm asked to find the inflection points and questions about concavity. So immediately I know I have to take the second derivative. So let's see, f double prime of x is negative. Let's see. If I look at the derivative up here, I'm going to have negative 2/3 x to the negative 4/3 minus 0. This is just negative 2 over 3 to the cube root of x to the 4th. Okay, so the first thing I realize about this is that this part is always positive because we're raising this to the 4th power, okay? And I also notice that I have a negative out here. So as long as x isn't 0, this quantity is always going to be negative. Okay, and maybe at 0 it's not, but you know, the derivative is always negative. Second derivative is always negative. So this implies that f is concave down on okay, so this function is really always concave down because the derivative is always negative wherever it's defined. And, or the second derivative, sorry. So that really answers the question, and there won't be any inflection points. Because in order to have an inflection point, the derivative had to change from positive to negative or negative to positive, but this derivative is never even positive. The last thing I'm going to do is I'm just going to quickly sketch the graph of the function. As I said before, I usually start by graphing the maxes and mins. So the local min is 0, 0. The local max that we got was 8, 4. And we happen to know that the function was decreasing. So also from the first part, decreasing, increasing, and then decreasing. And finally, from part C, we know that there are no inflection points. The graph is always concave down. So I just fill in the graph so that it's curving downward. So maybe that I don't want it to look like a max, right? The only max is going through here, and then it curves, the graph is curving downward. Maybe I'll make this a little more curved there. So everything is curving downward. It's never opening up like a parabola that opens upward. So that's a quick sketch of the graph.